Hi, we're going to cover a biomechanics problem today, and these types of problems end up being some of the arguably most challenging to set up. They're easy to execute in terms of the math. The equations are not that complicated, but setting them up tends to be the tricky part. And so we'll go through this sample problem in steps, and I'll encourage you to use those same steps as you do the homework this week, and certainly as you carry out a problem like this in a future exam or future biomechanics course, because you'll have problems like this in a course like that as well. The problem we're going to do is the one I ended up the lecture for this week with, and that's a sample problem of a person holding a weight behind them. You can see the problem in front of you now. Let's read through it. A person is performing triceps extensions with a 7-pound weight as shown in the figure. The triceps muscle is inserted into point B at an angle theta perpendicular to the arm. The arm is static at an angle alpha with respect to horizontal. Assume the arm weighs 15 pounds with a center of mass at point A. And again, I even prescribe the steps that I want you to carry out because I think they're the best approach to a problem like this. And the first is to complete a free body diagram for this case with all the dimensions and forces that are relevant here. And as I'll show you in a sec, those diagrams should be with symbols, not with numbers. This is where sometimes the textbook puts in numbers a little too early. And I prefer, and I think it's less error prone if we use variables to describe the situation. So I'll show you what I mean in just a sec. Then write down the equations of motion for that static situation, and again using the symbols. And then finally, once you have the equations manipulated in some useful way, then finally plug in the numbers and actually solve this usually straightforward equation for the force involved, which we're calling in this case Fm, and that will be the force M exerted by the muscle. So Fm stands for the muscle force that will be exerted at point B in order to keep that static situation, because you can easily picture without that muscle the arm would just fall down. The weight would bring the arm down, both the weight of the arm and the 7-pound weight that the subject is actually carrying. And now once we figure out the rotational aspects and assure that we have a static situation in terms of rotation, we also need to ensure that we have a static situation in terms of the joint reaction forces. So we're going to figure those out in a separate step as well. And that requires, again, a slightly different setup, and we'll go through that. So let's start with the free body diagram, and we'll try and draw one that's at least reasonably clear. As I've apologized for before, I don't have the wonderful penmanship skills of Dr. Christensen, but I'll see what I can do. So now we're going to draw a straight line here. I have a little tool that actually makes that into a straight line, which is kind of handy. And that's going to be our free body diagram that's meant to represent the angle of the arm. And so let's include some of that angle information with the line we'll draw here. We'll label these things in just a sec. The first part is really just to draw the diagram. And up here we have our fulcrum. You can draw it as a circle or triangle, whatever you want, just to make it clear that that's the case. We're going to have the point A, which is where the weight of the object is. So there'll be a weight from that point going straight down, a force going straight down relative to the weight of the object. And then slightly offset from that, we'll have another force, which is the force from the muscle, and it will head up in this direction. And then finally, we'll have the weight from the actual object acting at the end of the arm, and it will go in a downward direction. So that's our starting point for this diagram. Now let's add some arrows and some labels so that we have a downward force here. This is the horizontal, and we know we have an angle in here, which we're told to call alpha. Oops, that was pretty ugly. Let's see if I can make that more legible. There we go. Okay, and then we have our force here, which we're going to call Fm, and then we have a downward force here, which I'm going to call F of A, as in the force of the weight from the weight of the arm. Now we're going to have some other dimensions to worry about here. So let's go back and draw some of those in. So from this point, whoa, that didn't work out very well, to the point of application of the force from the muscle, we're going to have a line, and we're going to have another line from this point, and that's the angle between the force applied by the muscle and the weight of the arm itself in a downward direction. And then of course we're going to have a distance up to the actual fulcrum. And now we'll have some lines in between those to show those distances. So that's a distance, that line again. Okay, we have a line here, and then we have a line that will go up to the fulcrum there. And we'll give those some labels as well. I've called this A, this label, this distance here, called this one B, and this one C. And again, we want to use symbols as much as we can for this thing. It helps generalize the whole answer and the whole process. So it's quite useful. Now there's another angle we have to worry about. That's the angle perpendicular to the arm itself. And the arm, of course, is our lever in this situation. And that angle, let's draw it way up here, that angle here, we're going to call theta. So that's the angle theta. Okay, so I think, we need a force down here that's derived from the weight, the 7-pound weight that we're holding. And that should be everything we need for this part of the diagram, for the rotational part. We'll add the reaction force elements a bit later on. Want to think too about how the forces, say this Fw, is going to be applied to the lever. Sometimes it's useful to draw that as kind of a guide. So we can say here's the normal component of that force, and then we have a purely vertical element of force, which is this one here. That's where Fw points. This is just to give us some reference points here, and we can stare at this for a while and do a little math, compare perpendicular angles, and pretty easily convince ourselves that that angle alpha of horizontal relative to the arm is the same angle as we have here alpha, which is the angle between the vertical force of the weight and the normal direction to the arm. And we'll need that as we compute the various rotational moments of the problem. Now that's the diagram itself. Now we have to add in some variables that we know. So Fm is what we're trying to find. We can put that at the beginning or at the end. I like to write it down to remind myself. We know that the force of the arm, or the weight of the arm that's going to derive that force, is going to be 15 pounds. We know that the weight of the weight itself, the actual weight we're holding or the other subject is holding in their hands, is 7 pounds in weight. We know that the angle theta, we read from the text, is, whoops, that was pretty ugly. Let's clean that up. Is 80 degrees. Now we know that the angle alpha, which is the angle between the horizontal and the direction of the arm, is 45 degrees. And again, we just put these somewhere where they're handy. We can find them later. We also know some dimensions that are relevant here. We know that A, for example, is 2 centimeters. We know that B is equal to 10 centimeters. And we know that C is equal, B does not equal 10. This is why we should always check this over as we write it. So if we look back in the text, we see that I've got this completely wrong. So A is equal to 8 centimeters. B is equal to 2 centimeters. And C is equal to 10 centimeters. And this is a good time to look back at what we have here, make sure we have all the variables written down, check back with the problem, double check to make sure that we have the forces right, that the weight of the arm, for example, we go back and check that again. Assume the arm weighs 15 pounds with a center of mass at point A, so that we're going to call 15 at FA. FW, same thing, we're going to compare those. And this is just a good time to take stock. This is where errors can creep in. So have a look at that, make sure that you have all the numbers right, and then we can move on to the next step, which is to write down the actual equation. So this, you could argue, is part A up here. And now we're going to do part B down here. And now we have to stare at this problem for a while and recognize that we have a number of forces acting and which direction they're actually going to contribute moments. So we have this convention of counterclockwise rotation being positive, and then we have to create a diagram or a set of equations, excuse me, that reflect that diagram. So let's start with the force. It's always good to start with a force that goes in the positive direction. And we can picture, for example, we could start with the FW, that's the furthest one away. It's going to produce a counterclockwise rotation. And so the lever arm for that force FW is going to be the length A, B, and C all added together. So we're going to say A plus B plus C times FW. That will be the moment, but it doesn't, that's not enough because that FW acts in a vertical direction and we only want another perpendicular direction. We've already figured out that that angle we need to care about between the force direction and the normal is alpha. And so we can now say, with a little bit of trigonometry, we can now say that it's cos of alpha is the factor that's important there. Now we can do the same thing with the force Fa, let's say. Now it acts over a length c, and it is also Fa times, Fa times the cosine of that same angle. It's also directed vertical, so the same rules apply. So we have cos of alpha applied there. Those are the positive forces. Now what do we have in the negative direction? That obviously has to be balanced. In order to have a static situation, we have to have counterclockwise and clockwise forces. The clockwise force obviously comes from the muscle. So the muscle is acting over a length, and that length is B times C in this case. So B plus C, not times C. So B plus C, that's the lever arm. Then we have F of M. And now we have to figure out, oh, what's the normal component of that force? And we're actually nicely told that the angle between normal and the application of that muscle, the insertion of that muscle, is called the angle theta. And so we can write down cos theta for that. So that's the sum of the forces. I should have written that to start with. What we're doing here is we're applying this equation of the sum of all the moments is going to be 0. And this is the application of that equation for this particular case. So we're going to say that's equal to 0. Now at this point, it's tempting to start sticking numbers in, and there may be cases where that simplifies things. Who wants to drag around A plus B plus C? But I would argue not to do that at this point, and we'll see in lots of problems coming up in the course that it's going to be better to keep it in terms of symbols. And so now, and this is algebraic manipulation, we're going to put our Fm on the left hand side, and then we're going to see what's left on the right hand side, and we're going to have an A plus B plus C times Fw, and we're going to have a C Fa, and you might wonder what happened to the cosine of alpha, but the fact is that cosine of alpha applies to both these terms, so we can write it like this. And that simplifies things, so we don't have to compute cos alpha more than we have to. And then of course we have a denominator, which is the terms that come from the other side, and that's the B plus C times the ratio, or sorry, the divided by, here we have the cosine of theta. And we could even combine the cosine things, but that doesn't really simplify our lives all that much. Now we're ready to actually insert some numbers. So this is part B, and this went pretty quickly. It was a pretty obvious case. It's very easy when someone tells you how to do it, like I just have. But you'll find that this is sometimes one of the challenging parts, is to figure out which angles, which directions, which signs, which lever arms. So this is the part where you really have to take your time and then go again, stop, look at it, and check in with yourself and make sure that, okay, I've got A plus B plus C times Fw. That makes sense. I've got Fa times the length C. I've got those two cosine alpha factors. So just make sure that everything kind of makes sense with regard to the conventions and the situation in front of you. Because if you get this right, the rest will fall into place. So now let's go ahead and assume that we can set in some numbers. So this is part C, where we insert the values. So now we can say that f of m is equal to, and we can put some numbers in here. Now A plus B plus C, we look up and we say that's 8 plus 2 plus 10. And I really encourage you to write this out like this. It really reduces the likelihood of error. And then we look and say FW. Well, we can scroll up here again. FW is 7. Let's check that. Okay, so that's times 7. And then we can have the plus C, and C we know is 10. And then we have f of a, which we know is 15. So we have those numbers in place. And now we have, in that whole thing, we'll stick inside these square brackets here, and then we'll have cosine of alpha, and that's cosine of 45 degrees. So we'll write that like that. And then down here, we're going to have b plus c, and b plus c is 2 plus 10. And then we can stick the angle out here, and we can say this is cosine of the angle 80. And of course, you can do this in steps, or you can plug it all in depending on your confidence level. Sometimes it's good to do it in steps to actually write down intermediate results. That's we'll leave up to you, but at least you should have written out one step like this with all the numbers in place and then start calculating them. And it turns out if you plug in all the numbers, then you'll find that you'll get a number of 98.4. And then we look around and say, okay, significant digits, what do we have here? We're really not given a great deal of significant digits. Looks like you could even argue one significant digit would be enough. But I think 2 is safe. It's not completely outrageous. And in fact, I'll probably update this problem to include some more significant digits. So let's work with 2. And these are the kind of approximate calculations you end up doing, and we won't penalize you if you said this needs to be 100, for example, if you just had one significant digit. But if we stay with 2 significant digits, then we can say that the result that we care about is going to be 98. And now we realize, oh my goodness, we've forgotten units. So where are the units here? So you can insert the units in different places. Let's go back to this first equation where we sort of gathered things up. So this is this equation here, the FM equation. And then we'll say we have a length, A, B, and C are lengths, and those are lengths in centimeters. And we have to be careful, of course, that we converted those lengths into the correct inches, one could argue. But it actually turns out we don't have to, because as long as all the lengths are the same, they will ultimately cancel out. So let's see how that works. So we have A plus B plus C, which are all lengths, C, which is a length, and then B plus C, which is also a length. So we have centimeters on top and centimeters on the bottom. And then we have in each of these terms we have a force, which we've left in the horrible old English system of force derived from weight, which is in units of pounds. So here we have forces in pounds, FW, FA. So that stays on top as a force. And we can write that like that. So we have that on the top. And then the cosine angles, of course, they have no units at all. So we see that we're going to end up canceling the 2 length units. So it doesn't matter which units those were. So there's no need to convert them to be inches or some other unit of that you like. You can leave them in this sort of nice, round, small, sensible units and work with them in centimeters, and we'll still get the right answer in pounds. So we'll carry that foot-pounds over, and then we'll realize that that's our answer, 98 foot-pounds. And that's the correct answer for the value of f of m. Okay, so now let's move to the next part, which is part D here. And in part D, we're going to go back to our diagram first to have a look at it and say, okay, where do reaction forces occur here? Now, reaction forces are the forces that act on the body that you've decoupled, the free body. And so where would those act? Well, they clearly would act at, in this case, the shoulder, right? The shoulder is the joint where we have the rotation, the fulcrum, and that's where the arm attaches. So there has to be some forces applied there. And we don't know for sure what kind of forces those are or how they're applied. So I'm going to change colors here to try and make this a little clearer. So we'll have a force going right here that'll have some direction, and we'll call it the force of the joint, Fj. At this point, we really don't know what direction it will have, but it will act in some direction opposite to the sum of the translational forces that we have here. And because we have an FM that's going to be upwards and it's causing some lift and some move to the right, then we're probably going to have an FJ that's going to move to the left, and so we can picture that. And in fact, let's make a little more space here. So it didn't draw that very well, because we're going to have two components of this force that we have to also include. So we're going to have an FJX, so that's Y, and we're going to have an FJX, and those two are going to make up the actual vector quantity F of J. So those are the quantities we're going to have to deal with. Now, in anticipation of this, we have to figure out what are the x and y components of the forces of interest here. And so we see that Fw and Fa are easy. They're both in the y direction. So we don't have to do anything with Fw or with Fa. They have x components of 0 and y components that are equal to their original forces. The tricky one is F of m, because we have to figure out what its x component is and its y component is, and they look like that. And this is where things get a little bit tricky in terms of figuring out the angles of interest. So you can do this different ways. We need to find out an angle here, and we need to know an angle here, because those are the projection angles. They both add up to 90, so once we have one, we have the other kind of automatically. Now we can think about this different ways, and I can't really give you a simple recipe for this, but if we stare at this situation where the force Fm is applied, we can see that we have an angle theta between the perpendicular to the arm and the application of Fm. So that's theta. We've defined that already. And then we have these two blue vectors, which are x and our y components. And it doesn't take too much thinking to realize, and sometimes it helps just to imagine moving this a little bit and seeing what the effect will be, but that small angle between the vertical, the FMY, so let's call that FMY here, and this will be FMX down here. Now that small angle in there between FMY and the FM is going to be theta minus something, right? Because the whole angle between the perpendicular and Fm is theta, so it's going to be theta minus something, and it turns out it ends up being theta minus alpha. So the angle in there, we'll draw that like that, is going to be theta minus alpha. And that's really the main angle we need to know, because we know that if the projection or the angle between the Fm and the vertical FMY axis is theta minus alpha, then we know that this other angle down here is simply going to be 90 minus theta minus alpha. So it will be the remainder of the angle that we need to make that perpendicular angle between x and y, which we know has to be the case. So that now tells us what we have to write down when we're solving for these reaction forces. So let's go back to our part D here, try and keep that sort of in sight. So now we have D, in which we're going to apply the equation that the sum of all the forces in x is going to be equal to the sum of all the forces in y, and they're going to be equal to 0. And so if we start with, I don't know, F of x, we can say that the x force that we're really concerned with only has two components, because we see Fw and Fa have no x component. So we have a force F of m, and you can write this, of course, different ways. We can pick it as we want. Maybe the shortest way is to say that it's equal to the sine of that angle we decided we had up there, which is theta minus alpha, right? That's the angle that we had between the y-axis or the y direction and the angle itself, but if we take the sine of that angle, that will give us the x projection of f of m. And so we can go back here and write that down. Now we also, of course, have an fj component, so we are going to have fjx, and the sum of those will be equal to 0. We know that. So fjx is going to be equal to minus fm times the sine of theta minus alpha. At this point we can put some numbers in. We figured out fm before is going to be 98, and we're going to have the sine, and we know that theta and alpha, we can scroll up here again. What are theta and alpha? Theta is 80, alpha is 45. We look at 80 minus 45 degrees, and we can plug the numbers into that, and we'll get a number of minus 56 pounds. And again, the units here are quite straightforward because there's only units of force or weight involved, and so we can assume that there's nothing to change those units. So it's a pretty easy unit conversion to do here. So that's f of x. Now we can do the same for f of y. And now we have some other forces to deal with. We have the force from f of m, and this time instead of course, the sine, we're going to use the cosine because we're looking at the other component of theta minus alpha. And then we're going to have a negative component from the weight itself pushing down, another negative component from the arm weight pushing down, and then we're going to have the fj of y, and they're all going to equal 0. So that fj of y, that wasn't very nicely done, was it? Let's clean that up a little bit. Like I say, it's really important to try and be clear with your writing. You'll just confuse yourself in the end. So if that will now be equal to all the other things, all the other terms, so that will be fw plus fa minus fm cos theta minus alpha. Okay, now we can plug some numbers into that because we have these numbers from above. We scroll back up here and we see, okay, what are those numbers? Fw is 7, Fa is 15. So we have 7 plus 15, and we know that Fm is 98. And then we have cosine of that 80 minus 45. Okay, now we plug all those numbers in, and we'll get the number minus 58. Again, units of pounds, or force from pounds. So we have those two numbers. So now we know the two components of f of y, and we see that it's to the left and it's downward. And if we look back up to our diagram here, we saw that we kind of anticipated it that way, right? Pushing to the left and downwards. And that would make sense given the physics or the mechanics of the situation. So let's go back here and we figure out, now how do we determine that angle? Well, it turns out that the tangent of this angle, which we're going to call, let's say, beta, which is the angle of the direction of f of j, is going to be equal to fjy over fjx, and we can plug those two numbers in, 58 over 56. The minus signs cancel, we don't have to worry about that, and we end up with an angle of 46 degrees. So not surprisingly, given that the two x and y amplitudes are very similar, we get an angle pretty close to 45 degrees. And so that tells us that that reaction force up here, that points down and to the left about the same size, and so it have an angle of about 45 degrees away from horizontal, let's say. So with that we've solved the problem. We have all the pieces done, and we can call it good. So again, the trick here is just to be systematic, I think. If you look through all the steps here, they're nicely laid out. Even my diagram is a little cluttered, but the essentials are there. Using color can sometimes help if you have that available to you. I know it's not possible with pencils, but on paper at least you have a ruler to work with, and that can help clean things up a bit. But the main thing is we drew the diagram, we included all the parameters, we laid out the equations carefully, and that step B is really the one to focus your attention on. Once we have that set correctly, then it's really pretty easy to plug in the numbers and it is good to write the numbers in detail, check them again to make sure you got your A's and B's and C's right, and then carry out the calculation with your calculator and then come up to the conclusion. And again, the same thing with part D. The hard part was really laying out the equation. The hard part was figuring out some of these rather complex angle situations. So this whole configuration here with the complex angles in the X and Y directions, that's really the tricky part. And that's what you need to think about, need to practice on, redo these problems, different ways even. Maybe you try and figure out the other angle instead of the theta minus alpha. Try and use the other angle, the 90 minus theta minus alpha, and use the sine and cosine appropriately to solve the problem a slightly different way and show that you get the same answer. So the key point is that you can use these kind of questions for practice. I've laid it out for you here with answers. All the steps are there. Now take this problem in a day or two after you've had time to forget some of the details and just try it again. And the same with your homework problems. Once you get those back, just keep trying them over and over again until all this becomes comfortable and you recognize the parts where you have to focus, you recognize the parts that are kind of straightforward and mechanical, and that will all help you solve these problems both correctly and efficiently, because doing this in a reasonable time is important. And of course, this video is longer than the time that it would normally take me to solve this problem in order to explain to you what all these details were and why I was doing what I was doing. If you have questions about this, of course, get back to me, and I really hope that this will help you moving forward with the homeworks this week and with the midterms and exams to follow, which clearly will include these kinds of questions. This is an important element of our course. It's an important lead into the biomechanics course, so you will have to become comfortable with the concepts here and the practice here, and we're here to help you do that. Thanks so much. Bye-bye for now.